All right, so now it's time for our second session. So we'll carry on where we left off last time. We're basically reviewing some key concepts from Calculus 1. Specifically, we are learning about more advanced derivative functions, and then we'll also do some reviewing of integration, and then we can start the new material, which is Chapter 7, where we'll be looking at different types of applications of integration, mainly physics applications. And when that's done, we'll be moving on to Chapter 8, where we'll be looking at more complex integration techniques. So integration is a really large, complex topic. It will require a very long chapter all to itself. And so we'll be spending quite a bit of time with that because integration is far more challenging, in my opinion, than differentiation. And so you'll see, you can tell by looking in the book, there's a chart for integration, which is page after page after page of different possible cases. So we'll be learning a lot of those techniques. But anyway, in the meantime, let's get back to it. Now, by the way, I do notice that um, a lot of people have successfully signed into WebAssign, and that's great, but there's still a few people who have not been able to do so. So we're working on that. If you're having issues, you let me know, and I'll get in touch with Cengage, and they'll get in touch with you, and we'll get it straightened out. Um, it's at the start of any semester, there's always going to be some wrinkles, I guess. So as long as you let me know what's going on, and if the problems are going to last for a few days, I can always give you time extensions for your WebAssign problems because the due dates are set in the schedule, but I can always change them if necessary. And certainly one of the valid reasons for doing that is that you're unable to get into your own account. So in fact, just as a quick reminder, while we're talking about this, if you're able to log into your account, which I hope you are. Whoops, what happened there? Okay, now that's interesting. It's refusing to let me log in unless I've made a typo twice in a row. But I'm telling you, technology just doesn't like me. It's just unbelievable. Let me try that again. There you go. Who knows what was going on? So here's where we are. So you'll see there's a huge list of assignments. The only thing that's missing, I think I mentioned this the other day, I haven't quite finished writing the exams yet, so they're not in there, but everything else is here. These are all the assignments that are going to be due until the end of the course at the end of July. And I did mention that you are allowed to start early if you want to, but it's not necessary. However, having said that, actually, this is us here. So you can see what you might want to do here is in order to avoid running into problems, you see how they sort of categorize the assignments into past, future, and all. It's probably safest to just put all. Um, and then they're all listed here. You notice how we're starting with 7, then we're going to 8 and 9, and I'm saving 6 for last. This is our discussion about differential equations. So you can go in there and look at it and see what you're supposed to do, but the due dates are over here. Now, here we go. 6:15 is the first time you'll have an actual assignment. So you've got some time to work on these problems. I wasn't sure. I wanted to double check. And then after that, pretty much something will be due every week, whether it's these assignments or possibly an exam. So I'll let you know what's going on. But right now, this first 4 parts of Chapter 7 are here. And those will be due on the 15th, which is a Sunday night. They're all Sunday nights at 11:59 p.m. Now, also remember, you do have extra time available to, if you're willing to put up with a late penalty, 10% is the late penalty. And you'll get several extra days to work on it if you need it. like if you're just late or something happened, you just weren't home or something went wrong. If you have a more serious problem, like you've been sick or you're traveling or something, then you can request a longer extension if you need one, and I can take care of it directly from here. So, but just here's a don't forget about all this because we just started the course. We it's a brand new experience. Maybe you've never used WebAssign before. Just don't forget that typically these will be due every Sunday night throughout the rest of the course. Okay. All right. Anyway, so enough of that. And we haven't started this material yet anyway, so we can't do any of it, but we will start probably the next session. We'll probably wrap up the reviewing and then we'll get started with chapter 7. But right now, I just want to move back into the review that we were working on. And if you remember, we were working on a fairly complicated derivative example. In fact, we specifically were looking at the general power rule, which is itself an extension of the chain rule. So remember how the chain rule works. When you have a composite function, a function of another function, that makes things a lot more complicated when it comes to taking derivatives. So there's a couple of approaches we can take. Notation-wise, you saw that we used this first one. dy dx can be broken up into the product of dy du and du dx, or we can write it out like this: f prime of g of x times g prime of x. Now, I personally think this one is the most straightforward one, but that's up to you. And how does that work again? Let's just quickly review the case we were looking at last time. We have dy dx. Let me just copy this into my note sheet here. I'm sorry, no, y equals. By the way, the notes that I wrote last time are actually posted in Brightspace. If you look in there, let me go show you where this material. I just realized I should have reminded you where to find things in Brightspace. What I decided to do, I did create the videos. Last time, remember the videos were split into half. I had a technical problem that I had to get over with. So there's two parts to the last recording. And they're in Brightspace, but I realized that it's not in a very obvious place. So here's what I decided to do. I don't know why I didn't think about this sooner, but I've just created a separate category for the videos. So that way you don't have to search around for them. You won't look in there and say, well, where is it? What's going on here? I'd originally posted it under review. And I guess that kind of makes sense, but because it might not have been obvious. Look how far down it is. It might not be obvious that it's there. So instead, I created this separate category of videos. And so from now on, I'll be putting them in here. Now, if you look at my YouTube account, I did manage to get it in there too. There's a playlist in here. I'm sure you're all familiar with playlists. I mean, I had to learn how to do this, but here it is. And you'll see it's this one right here, MAT1510, that's us, summer 2025. And so they'll all be here as well if you want to look at them. Or if for some reason Brightspace isn't working one day, you never know what's going to happen with technology. They'll always be here as well. So there'll be at least 2 different ways of getting at your videos. Also, this website that I discovered last time by accident, I really think I'd like to keep this available at all times. It's so helpful. I didn't even realize it at the beginning, but look at all these different topics that are in here. It's a wonderful summary of all these complicated results. So I'm glad that we found this thing. So I'm going to keep it here in case we need it. It's called math.info, and it appears to be just a very detailed list of results so that you can find them when you need them. So what I mean, it has the product rule and it has the quotient rule and it has the chain rule. So you might want to make a note of this somewhere that it does exist. Now, unfortunately, I do see that they might be using slightly different notation. We don't want to get confused. So you don't have to use this website, but it's there if you want it. All right. So anyway, what were we doing? Oh, so this is an example of the chain rule. And so y equals x squared plus 1 to the third power. So you can see that this could be considered to be a composite function because you can imagine that, let's say, f of x. Well, actually, let's start here. Let's think of g of x as this function. And then you could think of f of x as g of x cubed. But the other possibility, which I think is maybe a slightly more straightforward approach, is to do it this way with the u of substitution. If we think of this as u, then we can think of as y as being u to the third power. And remember, the way this works is that the derivative can be written as dy du, du dx. And now all you have to do is differentiate these two and substitute them into this definition, and you're all set. So, for example, dy would be, based on the power rule, 3u squared. Du dx would be 2x. 2x plus 0, but we'll call it 2x. And then when you plug these into this expression, now then that last step is to replace the u with x squared plus 1. Set. I mean, you can still continue to simplify it if you want to, but basically you're all set. So you can see, I think this is a very straightforward way of using the chain rule, but of course it's not the only way. You can use other approaches if you prefer, but I kind of like this approach. So anyway, what they want us to do, there's another, the so-called general power rule, to distinguish it from the power rule that we learned earlier. Remember, the power rule very straightforward. The general power rule allows for the possibility that we're taking the derivative not of x itself, x raised to some power, but a function of x being raised to some power n. Okay, so that's a more general expression. And in fact, the power rule is simply a special case of the general power rule, where the function is simply x. And so you can see here, it's formally defined as this. If y equals u of x to the n power, then based on this rule, the result, the derivative is dy dx n u of x to the n minus 1 power du dx. Okay. So that is the general. And here's another way of writing. I don't know. I find the primes to be confusing. I like the du dx. But that's just, again, that's just me. You can use whatever notation you're the most comfortable with. Now you can see why this one is a special case where u of x is just x. Okay. That would mean that du dx is just 1. And so that's why, for this case, it reduces to nx to the n minus 1. So it is basically the same rule. This is the more general version. This is a specific case where the u of x is x. So then they're going to give us an example. 3x. Let's go through this one. Which, you know, if you want to use the du dy notation, You can simply call this y, just to be consistent. So we can call it y equals 3x minus 2x squared to the third power. And then u will be this inner function. Y will be u to the third power. And then du dx will be, we're applying the rules that we know to both of these terms individually. And dy du would be 3 squared. Okay. So the final result will be 3u squared, 3 minus 4x. Now, of course, we have to replace the u with its definition, otherwise, because we're not done. We need this in terms of x. So we end up with 3. We define u to be 3x minus 2x squared. The whole thing is squared. And then here we have 3 minus 4x. And that's it. Now, of course, again, it's always possible that we could, multiply it out and simplify it a little. But this is the right answer. If you put this into WebAssign, it should accept it. This is where you have to be a little bit careful. If not, you can multiply this 3 by these two terms. And of course, it's the same thing. So I don't know how flexible the WebAssign really is as far as this goes. So if you put in an answer like this and it refuses to accept it, why don't you go ahead and just try to multiply it out and see if that helps. And if you're still running into problems, just let me know and I'll see what's going on. If it took points off for something that's actually correct, like if it marked you wrong for this, for example, I can go back and give you the points. Okay. All right. Hopefully that won't be necessary. It's usually pretty good about explaining to you exactly how you're supposed to enter your answer. Now here's one where it's kind of the same issue here. You'll see that when you apply chain rule here, actually this is the product rule, but the chain rule gets involved as well. This is actually correct down here, but what they're going to have us do is simplify it by doing some factoring so that this is the answer that they come up with. Not that this previous one was wrong, but usually the rule of thumb in math is to try to simplify everything as much as possible. There are certain cases when you really, like, here's a classic example of this. When you're doing trigonometry, you might remember, like, if you ended up with something like this, you would never leave it like this. You're not supposed to have irrational numbers in the denominator of any expression. So you would engage in a process called rationalizing the denominator. Rationalizing meaning turning it into a rational number. And so how would you do that? You'd multiply this expression by, hold on. Something was crawling across my keyboard. I had to get rid of it. That's for sure. Just by multiplying it by radical 2 over radical 2, and you end up with 2 radical 2 over 2, which simplifies, of course, to radical 2. So, and by the way, also, I just want to remind you too, the reason for these names is because, if you might remember from your previous math courses, numbers like 1, 4, 9, 16, 25, 36 are referred to as perfect squares because their square root is an integer. Okay, so you might remember this from a previous class. These are called because their square roots are integers. And of course, integers are rational numbers. That's the whole point of all of this discussion, I mean. You might also remember, or maybe not, the square root of a number that is not a perfect square is irrational. So like radical 2, radical 3, radical 7, they're not rational numbers. So that's why we seek to avoid having those in our denominators. It's really no different than, remember, in really early days, if you ended up with an answer like 8/6, you would simplify it to 4/3. It's just a convention, and we want to keep everything as simple as possible. And among other things, other conventions is that we would like to avoid having irrational numbers in the denominator. So that, in other words, what this is all building up to is that here, these two answers are the same, but the web assign might require you to simplify it and bring it to this point. But I'm not sure. You'll find out when you're entering your answers. And so if you get something like this and you know that it's right, but it's marking you wrong, that might be what the holdup is. It might expect you to simplify it a little bit further. Anyway, so here they're doing basically the same thing with us. So why don't we try this one? It looks kind of challenging. We have x squared. Let's write it like this. X squared. No, I'm going to do f of x this time. Only because we're going to, well, actually, I'll tell you what no, let me change that to h. I'll tell you why, because we need to use the product rule. I want to be consistent with the way it was defined in the first place. And remember, h prime of x in this case is, no, hold on. F of x, g prime of x plus g of x, f prime of x. All right, so then that being the case, if f of x is x squared, or actually I'm going to call it h of x, times radical 1 minus x squared. You can think of this as f of x and g of x, because after all, we're now using the product rule. So then we have to figure out f prime of x and g prime of x so that we can carry on from here. F prime of x is a breeze, which is using the power rule. G of x, bad luck. We need to use the chain rule here. Okay, so let's see why. So let's rewrite this as y equals, let's treat this as if it were a separate problem. We'll call that y equals u is 1 minus x squared. Y is therefore, it's actually radical u, but I'm going to write it as u to the 1/2 power. So g prime of x is the same thing as dy dx, dy du, du dx. Oh, all right. It would help if we figured these out. Hold on. Du dx is going to be negative 2x. Dy du will be 1/2 u to the minus 1/2. Okay. So now we can make some substitutions. And of course, now the u has to be substituted here. Now we can simplify this a little bit. As you can plainly see, if I multiply these two terms together, rather, And this piece is actually the same thing as 1 over the square root of 1 minus x squared. So it might be easier to leave it like this. Okay, so therefore, um, when we go back to the original problem here, um, hold on a second. There we go. So our original f of x was uh, x squared. G prime of x is the result of this very complicated process. Negative x over radical 1 minus x squared. G of x is this piece, radical 1 minus x squared. And f prime of x is simply 2x. Okay. Now, of course, it's possible, probably it wouldn't be that difficult to simplify it just a little bit, but yeah, see, they decided that they wanted to consolidate all into one term, and we could certainly do that. But I mean, this is it. Okay. So anyway, let's see what's next. Oh my God, here's another one. All right. Well, I'll tell you what, we don't have to do every single one of these. If you want to go through and review these on your own, you can. We want to move on because we do have new material to cover. Let's move on to the trig functions and the chain rule. Now, all the rules we were seeing earlier involved sine x, cosine x, et cetera, et cetera. And those are right here somewhere. Um, okay. Well, I'm not finding it now. I know that we're here. That's the problem. There's so much good stuff here. It's hard to find what we need. All right, I'll tell you what. Let's go look at it. I'm sure we could find another table. Yeah, so we saw this the other day. The derivative of sine of x is the cosine of x. The derivative of the cosine of x is negative the sine of x. We can use this as a starting point for all the others because remember the other uh, trig functions are all functions of these two. So by using the appropriate rule, we don't really need any more. I mean, it's nice to have a table, but we don't absolutely need it if we understand how this works. But once we get involved with functions of x, then suddenly the chain rule gets involved. So they want us to see that here. And remember, this is why it's the notation can get a little bit annoying here. U prime is being used to represent du dx. Okay, so in other words, the derivative of sine u, according to this table, is Oh, wait, sorry. I think I wrote it wrong. Sorry, this is X, yes. Is going to be, now it's going to be the cosine, of course, but it's not just the cosine. We also need to take into account the fact that this involves the chain rule. So it's going to be cosine u du dx. Okay. And the same thing will apply to all of them. So in other words, like you saw um, the other day, we had the secant of x, secant x tan x, but now because u is a function of x, we need the chain rule. So for example, y equals the sine of 2x. Let's just quickly start with that one. So then we think of u as this 2x, du dx is 2. So the derivative, y dx, is the cosine of 2x, because this is u, but then we need this as well. Okay, so therefore we end up ultimately with, and usually something like this, you would move the 2 to the front. Okay. And so that's how that works out. Here they've got cosine x minus 1. So remember the rule here, when you're taking the derivative of the sine, cosine rather, that equals the negative sign. Okay, so you're going to have negative sine x minus 1. Now du dx is just 1, so you can just write it like, leave it like this. And then the tangent, so if you remember, well, of course, you may not have this memorized, and I guess there's really no reason why you should, but the derivative of the tangent, according, no, not this one. Oh, that's right. This is the one we never did find that table, did we? I must say, this is another very impressive website. I'm going to make a note of it somewhere so that in case we need it again. But I thought it would be a simple matter to just find a chart. You know, sometimes searching for things is like pulling teeth. It really is. Well, Mr. Artificial Intelligence gave us our chart. All right, here we go. So for the tangent, it's simply the secant squared of x. I don't know why that was so hard. I mean, really. So that means you're going to get, and you're done. Okay, great. I'm just going to move it up there to get it out of the way. All right, so that's that. Now, oh, that's right. They gave us this little summary table. Now again, you notice how they changed the notation again. Just be aware, like you notice how they've got the product rule listed like this. Let me just show you what they're talking about. So here's our basic product. Oh, sorry. What they're doing here, maybe just to make it easier to memorize it, is that if we think of um, u is f of x, g, v is g of x. Then you can think of u prime as f prime of x, and v prime is g prime of x. So this could be reduced to, if you start with, they're calling it uv. If you're thinking in terms of primes, you could write this as y prime equals, with the understanding that u simply means the f of x, v prime is g prime of x, v is g of x, and u prime of x is f prime of x. It's the same thing, only u's and v's instead of f of x and g of x. So, um, it's up to you to decide how to remember this. So it looks like they're consistently using u's and v's here. Oh, here we go. Here's the table we needed a couple of minutes ago. So this is for x, though. Once we have u of x or some function here, then we need the chain rule. All right, so that's enough of that. Let's see, there's one more section here. This one is a little different. This one's a little bit trickier. It's probably been a while since you thought about this. This is something called implicit differentiation. And what happens here is that we may have a function that is so complicated that we can't separate out the x and the y from each other. You do run into that sometimes, or at least it wouldn't be easy. So there are rules set up to let us take the derivative anyway, and it's called implicit differentiation. So what they're making a point here is that if our equation is written where both of the variables are on one side, you notice how normally we expect to see the function as y is a function of x. That's not the case here, is it? It is not. It's implied. This y equals 1 over x is implied by this equation, but it's not shown to us directly. We call this implicit form. We call this explicit form. Most of the time, our equations are written in explicit form. And if they're not, it's usually not that difficult to rewrite them so that they are in explicit form. But sometimes it's not. It's either not easy or it's not even possible. And then we need to do something a little different. So let's see. Now here's one. Let's see how this works. So the function is x squared minus 2y cubed let me turn this off. Plus 4y equals 2. So we'd like to know dy dx or y prime. So here's what we're going to do. What they're telling us here is that in this case, when you're differentiating with respect to x, when you run across terms that contain either constants or x's only, then the rules are the same. It's when we find ourselves needing to take the derivative of some function of y with respect to x that we need to change our approach. We have to use the chain rule. And then some books use slightly different notation here. Some books replace the dy dx with y prime, so you just need to be aware of that. So for example, I'll tell you what, why don't we follow this example right here, since they worked it through all the way. I think this is the best example. The derivative, we'll get back to this one in a minute. The derivative of xy squared is this. Now, we're here just simply using the product rule, by the way. So if you remember the product rule, if we define it in terms of h of x and then when you differentiate, you end up with this. But I did it again, right? Sorry, that's supposed to be f prime of x. So in other words, you could think of it as the first times the derivative of the second plus the second term times the derivative of the first. That's exactly what's happening here. So it's the first term times the derivative of the second plus the second term times the derivative of the first. So this takes the place. This x is the equivalent of f of x. This is the equivalent of g prime of x. This is g of x and f prime of x. Now the question is, what happens when you differentiate y squared with respect to x? That's the new part. We haven't seen this before. That's where the chain rule gets involved. And so what happens is, let's take this down and look at it separately. So it is a chain rule problem. What you're going to have here is so in other words, if you were taking d dx of u squared, so it's the same thing. It's just that it's y instead of u. So this piece comes up here, right? Let me make sure you can see what I'm doing. And now, after making that substitution, we should be all set. Okay, so in other words, we have x, and then we have 2y dx plus y squared. Now, d dx of x is simply 1. Okay, so therefore, we end up with 2xy dy dx plus y squared. Okay. So, and that's the final answer, by the way. Now, you might be asked to do other things with this result, but that the actual is the result of doing implicit differentiation. Okay. So for something like this, then you're going to take the derivative of each term separately. Equals zero because if you take the derivative of any constant, it's just zero. So for the terms that involve just constants or x's, we do not need the chain rule. For the terms that have a y in them, we do need the chain rule. So the first term would simply be 2x. Now this one is going to be 2 times 3y squared dy dx. That's the chain rule. And then here, okay. So now we can do a little algebra. Track this from both sides. Now I've got a common factor here of dy dx. And so ultimately I can just simply divide that out. And there we go. Wow, that was tough. That was a tough one. Okay. Um, now, let's see. Okay, look at that. So, all right. Anyway, like I said, I don't think we need to do every single one of them. We just want to make sure that we understand the basic idea. And then if we see it again in Calc 2, the actual Calc 2 notes, we'll review it when we get to that point. All right. So it looks like we're kind of done reviewing chapter 2. Now we can turn our attention to integration, which of course, as you know, is the reverse of differentiation. It's like you're basically reverse engineering the differentiation process. So let's get, this would be chapter 4 in the first part of this book. So we're going to run through and remind ourselves of the basic rules of integration. Yeah, I mean, wow, this session went by very fast. The next session will probably be enough to wrap this up and maybe take a quick peek at chapter 7. The actual applications of integration, but for today, we're just going to carry on. And so we start out with the notion of antiderivatives. Now, antiderivatives and integrals are the same idea. Most calculus books introduce it as an antiderivative just to reinforce the idea that it's the reverse of the derivative. But then normally we just keep using the word integral from that point on. So what they're saying here, now we have to watch it for the notation too. Capital F is normally used to represent an either antiderivative or integral. So in other words, if we have some function, now they're telling us that it's x cubed. All right, so we start out by assuming that our original function is x cubed. So the antiderivative of 3x squared, well, you would think it's just x cubed. but technically that's not correct. It's x cubed potentially plus some other constant. Okay, why is that? Because the derivative here is also 3x squared. In other words, it doesn't matter what the constant is, and it could be zero. There's an entire set of functions, each of which has the same derivative, 3x squared. So when you integrate, unless you have other information, it's impossible to know which one you started out with. So we normally write the c here to remind ourselves that there potentially could be some constant added to our original function. So we ended up still with the same derivative, in this case, 3x squared. So in other words, so the constant, this one has an implicit constant of zero. So in other words, no matter what the constant is, the derivative is always 3x squared. So the antiderivative or integral of f prime of x is going to be written as x cubed plus c, just to indicate that there might be a constant. Okay, so that's the part that we never want to forget. In fact, if you look in the WebAssign problems, I noticed that all the ones that involve integration, they always put in parentheses, don't forget about the constant, because and then it tells me that if you do not put in the constant into your answer, it will mark you wrong. But it's trying to help you by telling you that. So with that as our starting point, and by the way, sometimes you see this capital F is used to represent the antiderivative or integral. Okay, so here you could write, for example, just a reminder, capital F is an integral or antiderivative. Lowercase f is the original function. F prime of x is a derivative. So with all that being said, there are many, many rules that we need to be comfortable with for integration. And again, like I said before, this is going to be messier than differentiation. So yeah, so they're telling us that a g is an antiderivative if it takes the form f of x plus c. See now, here's what they did. I don't know why they like to jerk around between the different notations. Remember way back we discussed that the derivative could be written as f prime of x y dx. It can also be written like this. So that's a derivative. So if that's the derivative, then the antiderivative, the integral, must be x squared, the original function, plus c. And c is, as you can probably see there, is the constant of integration. And we'll get to this later on, but this involves us with uh, differential equations, but we won't be doing this just yet. We'll be getting back to that in chapter 6. So in other words, a differential equation typically has x's, y's, and y primes, or dy dx's, all mixed together. And ultimately what we're trying to solve for is the derivative, or the integral of dy dx. So here's one where dy dx leaves us with 2. Integration brings us back to 2x because the derivative of 2x is 2. But then we need to include the c, and they're calling that the general solution. This is a specific solution where the constant is 0, but we normally write it like this, the so-called general solution, just to make sure we don't leave out the correct one. And they're showing us that, yes, all of these are straight lines, and they all just have different intercepts. If dy and dy dx is formally defined, if it is written as f of x, then we can rewrite it. And these, by the way, these are known as differentials. And just think of these as similar to deltas. So in other words, the delta x is a small change of y. The dy is an infinitesimally small change of y. Delta x is a small change in x. Dx is an infinitesimally small change in x. Okay, these are called differentials. So this is the what we're going to be doing here. Y equals, if we, this is the integral symbol. And intuitively, and we'll see this later on, it could be thought of as an infinite sum. Okay, so that's how the symbol evolved. Apparently, it's sort of meant to show like a sum. If you remember, this is our summation operator. You can imagine if you stretch it out, it suddenly becomes the integral sign. But integral means there's some infinite sum taking place here. So the formal notation is that y equals the integral of f of x dx, whatever the answer is, it's written like this. This is the formal notation for taking an integral. And this implies that if I differentiated f of x plus c, it would bring me back to the original function. And now we're ready for some rules. Okay, but I see that our time is basically up. So I'll tell you what, I think it makes sense to start right here tomorrow or the next day. It'll probably be tomorrow that we'll have the next of these recordings. And certainly by tomorrow night, this should be ready. So we'll start with these basic rules, refresh our memory about how they work. And soon enough, we'll be ready for the new material, which, like I said, is chapter 7. By that time, it'll all be fresh in our memory, and so it'll make perfect sense. We don't want to start the new material if we don't remember what integrals are, because the whole point of chapter 7 is to use them for different applications. So hopefully by the time we're done with all this reviewing, we'll be ready to roll into chapter 7. So we'll stop it right here, and then I'll see you next time. Okay, and also, like I said, if you're having issues with the technology, just let me know and we'll get it fixed as soon as possible. All right, so bye.